So, I'm Gerd Hoffmann. I'm working for Red Hat, and I want to talk today about how the guest display will actually show up in your desktop window, how all this is working together in QEMU. So I'll first give an overview how it's working, how all the pieces we have in QEMU are working together to get it done. Then have a short view into the actual code. Then give a preview what I'm planning to do in the future with getting accelerated graphics working in QEMU with the help of OpenGL and the virtio-gpu and the virtual project which is ongoing. And finally, a demo. And by the way, the demo is already running. The demo is running in a virtual machine, which is using virtio-gpu. And you can see it's a bit more smooth than you maybe know if you're using Spice or VNC, because it's running with OpenGL enabled already. So let's start. How it looks like. We have on the guest side, we have the devices the guest is seeing. The default configuration, it's a Cirrus VGA. We have a PC keyboard and mouse, and usually also a tablet. So you have the absolute coordinates for your guest. Then we have the QEMU console code, which has a display state. The display state is basically some kind of umbrella to keep track of a number of QEMU console structs. And your QEMU console is basically a central data structure where QEMU keeps the display state. And we have two kinds of display QEMU consoles. The one where the graphics devices are connected to on the top, and it's also possible to hook up character devices like a serial line or the monitor using this VC character device, which is also hooked up to a QEMU console, where the VC character device will do the actual rendering and also put it the output on a QEMU console. So you can see if you start an QEMU with SDL display in a default configuration, you can hit this Control Alt and a number key to switch between those consoles. And the same with VNC. And then you have the actual user interface code, which can be the VNC server. This can be SDL, where we have SDL1 and SDL2. And the user interface will interact with the core display code using a display change listener, which is a structure which is used to notify the user interfaces about any changes coming from the guest all the way down to the user interface. And finally, we have the VNC client connecting to the VNC server, showing the bits to the user. Or in case of the SDL interface, we have a window where QEMU is showing the content directly. And one thing which is new in the SDL2 interface is that you don't actually switch, but it can show both QEMU consoles at the same time. This wasn't possible in QEMU a few releases ago. We have some thing called active console in QEMU, which points to one of those QEMU consoles, and the VNC server is still following the active console. So if you switch with this Control Alt number hotkey, it will switch between either this or this QEMU console. But with SDL2, you just get a second window for the second QEMU console, and you can see them side by side. So you don't necessarily have a one relationship between graphics card and QEMU console. The upcoming virtio-gpu graphics card is able to support multiple heads. And this is done by simply having two QEMU consoles registered by the graphics device. And of course, you also get in the user interface, you get a second one more window for the second head, which can be turned on and off, depending on whenever the guest is using that head or not. It looks very similar if we just plug in a second graphics card, which is possible for quite some time. We got a secondary VGA, which isn't actually a VGA card because it doesn't occupy the VGA ports. It has an MMIO bar instead, so you can, so it doesn't conflict with the VGA ports, and you can put it into QEMU and have a second display device this way. And this will also register a QEMU console, which again will show up as window in SDL2, or if you're running with the VNC server, you can have one more console you can switch to with the hotkeys. And if we are that far, that's only a small step to get a full multi-seat set up. We only need a second set of input devices, which we can assign to the second VGA, and then have to set up the routing of the input events, which are coming back from the user interfaces. So QEMU knows which can figure out which input device should get the input events depending on from which window the events were coming from. This is the way you are doing it. You can create, this is the second graphics card you can add, which gets an ID, and if you're adding the USB cable and USB tablet, you can specify those two belong to this device, and QEMU will get the input routing correct. And to make the configuration inside the guest a bit easier, we add also a PCI bridge and put all the devices below the PCI bridge. And then it's on the guest side just a single UDEF rule to teach systemd that you want to have a new seat created from those devices below this PCI bridge. And then you will get a GDM login screen on both graphics cards. So if I look into the code, the virtual VGA card is responsible for creating those QEMU consoles with this function call. It passes the devices and also passes some a number of callbacks in this graphics hardware operation struct. And there are a few more, and the most important callback is the update callback, which can be used by the core console code of QEMU to ask the graphics card to update the screen. This is the other side, the user interface. This will also register a number of callbacks, the display change listener operations. We also has a refresh function, which is called in regular intervals by a timer. And also the most important functions are, again, the update function. And the DPI switch function is used to switch the backing store of the graphics display, which happens, for example, if the guest switches to another video mode, then we have to inform the user interfaces, oh, no, the video data is somewhere else now. And this is this example is taken from VNC, and this is just following active console. And the SDL2 code is doing it a little bit different. It's a single line which is different, where we can say this display change listener should be pinned to this console, and it just loops over all the consoles which are present in the system and creates registers a display change listener for each of them, so it can display the windows at the same time and get updates. It gets them all updated. So here's how this all works together on a full update cycle. In the core code, there is a timer function which is called at regular intervals, which goes call the refresh function of the user interface, in this case the VNC server. And the VNC server then will ask for a graphics card update, which the core code will again forward to the guest display emulation. And then the VGA emulation typically goes checking the dirty bitmaps to figure out which areas of the screen the guest has updated, and will send and again call debug graphics update for those regions. And if there are more than one region has been updated, it can give you multiple of these calls. And VNC will collect which screen areas have been updated. And when the call finally returns, it then will go push all those changes to the VNC clients. And the callbacks coming from the console call code to the user interface and to the guest display go through those callbacks registered, which we have seen on the previous slides. So one important thing is the display surface, where the actual data is stored. These days, this is basically a very thin wrapper about a Pixman image. And this is a function which is called by the VGA code to set the display surface, which typically happens on mode switches. And there are a number of different ways to create such a display surface. The easiest is just create display surface. Those display surfaces are backed by host memory, so QEMU will just allocate a block of memory for this Pixman image. And then it's the job of the display emulation code to fill in the data it has into this display surface. And this is typically done if the guest display can't directly handled by Pixman. For example, if the VGA is run in text mode, the VGA emulation code has to do all the text rendering using the font uploaded by the guest. Once the guest has switched the VGA into graphics mode, we can usually just use the frame buffer created by the guest directly. And then you can go for this version. And you just pass in a pointer and say which size the surface is and which format it is. And you get back a Pixman image which is directly backed by the VGA memory. So we don't have to copy around the data. If you want the user interface code update the display, we just have to notify the user interface code about which areas have been updated. This is a very similar one, which can be used by ARM stocks, for example, where we don't have dedicated device memory, which is used for the frame buffer, but just normal guest memory. So this is very similar to this one, except that this will automatically handle the mapping and unmapping of the guest memory. So for complete lesson, the input event routing, the virtual hardware can, if it finds a property set, which you have seen on the command line, it can call the input handler bind function to say that this input handler should be linked to this device and possibly to a specific head. In case of a tablet, this is interesting. If you have a multi-head setup, you need to know from which head the mouse event is coming. And then each time an input event is sent to the console core, the console where it is coming from is passed to the console core. And the input code basically uses the QEMU console just as tag where the input event is coming from to figure out to which device it should go to. So the console code isn't directly involved there. It's just used as to indicate where the event was coming from. So now to the accelerated graphics section. A number of reasons. We already have OpenGL code in QEMU today. And this is for this small box, which exists as a virtual machine model in QEMU. And that has a texture mapping unit for video effects, and this is actually emulated by using OpenGL. And today, this happens by just copying back the data from the OpenGL texture to a display surface. And of course, we want to do it possibly in a more efficient way. Next reason, of course, is the virtual project or virtio-gpu with 3D support, because every modern desktop these days uses OpenGL for rendering. If you have your modern GNOME desktop, or Firefox browsers also using OpenGL for rendering. So it's important to get hardware acceleration running so the user interface is running more smooth and it's running in a virtual machine. And the third reason, we have just seen it 2 talks back, Intel is working on, or has it already running, to virtualize the Intel GPU. And of course, we also want to integrate this somehow. So you don't, as it was told, you don't have to, can only route it to an external monitor. You can also take the picture somehow. We have to figure out the details yet and pass it on inside QEMU. So the display from the Intel VGPU can also show up in a window either locally or remotely. So to handle that, we have to add some OpenGL support to the console core. First, we need a bunch of functions to handle OpenGL contexts. This is because you can only set up OpenGL once in a process. So we can't have the rendering code do its own initialization and have the SDL code also do its own OpenGL initialization. And that's why we need this set of functions. So if you're using SDL to display the guest display on your screen, you also have to use SDL and ask it to create a context and so on. And that's why we need those callbacks to manage the OpenGL contexts. And then again, we have OpenGL variants of the functions to define where the guest display is. And this takes just an ID, which is a texture ID at the moment. And of course, the size and the location of the guest display inside this texture. And finally, a function to tell the user interface that this area of the screen should be updated now. And this is how this works with virtio-gpu. So we have the virtio-gpu interface. We have the updated QEMU core in the middle. Also the SDL2 user interface, which is the only one supporting OpenGL at the moment. On the guest side, we have an application running using OpenGL. It goes to the OpenGL commands go to the Mesa library, which translates this into a Gallium command stream. Gallium is a Mesa internal representation of the 3D commands. And what we are doing now is going past through this command stream through the kernel driver, through the shared library kernel driver with virtio-gpu to the render library, which is again part of the Mesa project. Dave Ehrlich is working on this library. And this again is using OpenGL to render the output. And here again, you have a Gallium command stream, which looks a bit different, of course, because the texture ISDs have changed and so on. Then it goes to the hardware-specific driver and will finally show up on your screen somehow. And of course, the virtio-gpu device has to talk to SDL to tell which texture the guest display is on, and SDL then has to also talk to libgl to ask to blit this texture to the screen. So there's some communication between those components needed, but the basic idea is to just take this pre-processed OpenGL commands in form of the Gallium command stream and pass them through to the host and process it there. So what is working today is what you can see here. We have the virtio-gpu working with 3D acceleration, and at the moment it's only working with the SDL2 interface. So we have a long list of stuff to do. I want to integrate this funny Milkymist texture mapping unit. I also like to integrate the VGPU stuff done by the Intel guys, that you can have your VGPU display in a window. We need OpenGL support in the GTK user interface, of course. We also want to be able to render without an X11 display. So if you need an OpenGL, if you need an XL display, you bind your virtual machine lifetime to your desktop session lifetime, which is a bad thing. And if you want to decouple that, you must be able to render without X11. And this should be working by rendering using render nodes, which we got in Linux recently, and then render the image into DMA buffs, and then start passing around those DMA buffs to an external application to show the guest display, and someday also integrate this with SPICE, probably with a new display channel type where we can pass around those DMA buff handles. So SPICE will not accept those QXL commands for the display, but will instead just take a DMA buff handle and build this to the screen. And of course, once we have this handling with passing around DMA buffs, it would be also nice to have the classic code path using the display surfaces without acceleration. Also put the output into those DMA buffs and handle and pass them around, so we don't have to copy the data around in the local case. If you today use VNC or SPICE to show the guest display, even with both QEMU and the viewer running on the same machine, the data is still going over the socket or over a pipe. And if you're passing around DMA buff handles instead, we can avoid that copying. A tricky one is to get the remote display working. Of course, we can just read the rendered result from the texture, like we read from the display surface today, and then encode it using the existing code paths and send it over to the network. But of course, that's not the most efficient way to do it. And the problem is how to do it better. From a technical point of view, it makes sense to just encode the whole thing as video stream and send it over the network this way. The only problem with this is the pattern situation, because the hardware we have today tends to support H.264, and we all know the situation of playback and the codecs patterns, and that isn't so easy to just ship a decoder. So that's a bit problematic from this point of view, even though it makes a lot of sense from a technical point of view. So
not the only problem. H.264 is not use quality. Right? It's not pixel perfect. So for a desktop, it's annoying to use a video codec. Basically, you don't want to use a video codec. For gaming, yes, but for desktop, no. Like if I send you a JPEG image of my desktop, you won't be happy.
But yeah, I would expect that if you have not so much updates, the codec will increase the quality, use the bandwidth it has to set a better quality image. So even if you get a not so good image for the first showing up of the window, it should get better over time. Yeah, but
and also
right now it's just an idea. I don't have tested out how it works.
The other problem is we don't know if the hardware supports for many VM, because remote VM, you don't want to have only one VM in the host. So if you have only one encoder, it's not going to scale. That's the question, also one question.
Yeah, as I said, it's to be investigated how to solve this best. This is just one of the ideas, and I'm welcome to listen to better other ideas. It's not an easy thing how to get this display to a remote machine, especially if you want to have high frame rate right? That you actually can feel that it's better than just the classic VNC we have today. So I think that's, yeah, I have one more thing I want to show. A bit more than just a web browser. We have this, oops, where's my mouse pointer? Disappeared. Oh, there. I'm single player. That's and let's go. Oops. And then you can go on and oops. I haven't trained this.
Good to see I'm not spending all the time on that.
But it shows that the performance of the 3D performance is pretty well. Oops. Okay, I think I just switched over. I have one last slide, which is with a number of links. So, any questions?
So I guess you don't plan Windows support anytime soon because of the ESA binding.
I have no idea how difficult it would be to create a Windows driver. Dave, who has written this running library, thinks it is possible to do it, but I have no idea how much work it is. So I can't really comment on it.
Basically, the problem which you applied like to be think about is the problem which is faced by many other remote display applications. VNC is one of the classics. They have the same problems. Delivering the stream, the graphic primitives to remote display. I guess that modern X11 system, which will be called the next one, which doesn't have this remote display ability from the beginning. You have the same problem because it's two links on the same three-dimensional world from the beginning. Is there any collaborations between what we are doing and what other projects are doing? We have the same problems to solve.
Not at the moment. For VNC, we have just a VNC server in QEMU, but
VNC, if it is to go for not to stay like it is, but to develop. Okay. The same problems and other projects face the same problems. You see, VNC is just one example. And it's not just QEMU, which so we need, I think, we need to bring together these problems with X remote display context too, the same, and use the same algorithms maybe.
Well, one problem is the classic approach which X is taking doesn't work very well with modern systems because they transmit all the gigahertz operations to the client side, which works pretty well, or worked pretty well 20 years ago, where you had pretty simple displays. And these days, we basically have full screen animations. It doesn't work anymore. And you need something else which scales better. So yeah, I think Wayland basically has the same problem for remote display, and it didn't follow that closely what they are doing in this area. But yeah, it's possible, and it's a possible solution to look at the Wayland protocols and see if it's usable to send over the displays. Well, we basically always have a full screen, a complete display we have to send over. And because we want to do all the running on the host, because sending over all the resources to the other side and let the client side do the rendering just doesn't fly, because it's too much data. And so a video codec looks like a natural thing because they have a very similar problem, and if it doesn't change much, they can detect this. This is all in there. But of course, yeah, you have this display quality problem because video codecs weren't designed with desktop screens in mind. So it might not be the perfect solution, of course, yes. And it's still to be done.